As we wish to estimate the percentage of U.S. adult population that has hyperthyroidism. You guys know where the thyroid is on your body? Yeah, it's right here. You want to know how big it is? It's a little guy. It's a little tiny thing.
Isn't your thyroid just your muscles?
It's right by it. So it's I tell you what, it can wreak havoc on your body if it's not working appropriately. And for the gentlemen in the room, I will just tell you, at age 40, most males' thyroid will stop working. And you don't know it stops working until they do this big old blood test. And then they start giving you ground up pig thyroid for the rest of your life. Kid you not. Yeah, there's a whole bunch of different ones. I choose to take the one that they've had in circulation since the 1960s. They're like, oh, we got a better one. This one's got a lot of data. All right. A random sample of 400 U.S. adults shows that 46 have the disorder and require medication. Okay. So, what is the population of interest? U.S. adults, right? U.S. adults is all you have to say for number one. Population interest is U.S. adults. And then what is the sample? Sample is 400 U.S. adults. Those were two tough questions, I'll tell you what. Maybe I should make that whole test just like that. Yeah. And then what is the point estimate as a percentage? Okay, so the point estimate as a percentage, so for number 3, you're going to try and make this work. Number 3, you're talking 46 out of 400. And so 46 divided by 400 is going to be basically 0.115. Okay? And then constructed night. Yeah. Oh, if I made a percentage, it would be 11.5%. So either of those answers, right? Hey, that board isn't on, and I didn't even realize. I'm writing stuff down, nothing showing up on it. I'll tell you, can't take me anywhere. Well, take me to Disneyland. That'd be kind of fun. Universal? I would like to go to Magic Mountain again. I always thought that was fun. Or Cedar Point in Ohio.
Can we have a field trip?
Yes.
All right.
Let's do it. Field trip to Elitch's.
Already got the form signed.
All right. I like this. And then it says construct a 95% confidence interval to show your setup. Okay. So the 95%, you're going to take your point estimate, PE, and that's going to be plus or minus the normal distribution, 0, 1, and then period inverse CDF. And then remember this is going to be the halfway to 100. Okay, so they want us to create, if they wanted us to create a 95%, halfway to 100 from 95 is what? 97.5, and 97.5 is 0.975. Okay? Does that make sense? Okay, so that's just a big thing. And I will tell you, this was the first place I had ever heard the halfway to 100. And I think it's genius. Thanks to Mr. Anderson for pointing that out to me. I remember it because it's a little longer drawn out if you don't understand that concept. Yeah.
In the parentheses, like after normal
distribution. 0, 1. Because we don't know what the parameter in the standard deviation necessarily be. You?
Will we change PE to 0.115 or 11.5?
It'll be 0.115.
Cool.
Yeah, so, all right. So let's go to, there's my mouse. All right. Hey, there's Schoology. So, Desmos. All right. So, normal dist, 0, 1. Okay, good so far, everybody? And you don't have to worry about making the normal distribution appropriate because you're going to go inverse CDF. And your halfway to 100, we said, was 0.975. All right, so that comes out to 1.96. Agree? So that 1.96 is our Z star value. Okay? So that 1.96 is our Z star value. So if we go back here, this part right here becomes 1.96. Okay, so we're going to go 0.115 plus or minus 1.96. And then, oh, I forgot the other part. Then we have to do the square root of our percent, 1 minus our percent over our sample size. So if we figure out what this is, P, 1 minus P over N. So our P is 0.115. 1 minus P is 0.1, that, divided by our sample size, which is 400, and we take the square root of it. So if you did that a little bit of arithmetic, you would find that comes out to 0.0182. So then you get 0.115 plus or minus 1.96 times the 0.0182. And if you do the math appropriately by adding and subtracting that, just doing a little algebra, that's going to go 0.079 to 0.151. Or you could say that it goes from 7.9% to 15.1%. Okay. And again, I'm going to re-emphasize this because it's important that you understand this. This basically means that we are 95% confident that if we reassessed a sample of 400 patients, that our new mean of that new thing would fall between 7.9 to 15.1% of the population of our sample would have this particular disease. Okay, it's a weird thing to think about, but you're just trying to figure out. It's like, well, what is the actual estimate? I don't know. I'm 95% sure it's going to fall between these 2%. Okay, well, what happens if it doesn't? Well, that means there's a 5% chance it didn't. So that's something where we will eventually get into something called the type 1 and type 2 error eventually. But we're not quite to type 1, type 2 errors yet because we haven't even created hypotheses and stuff like that. All right. So number 5 says, does the confidence interval provide evidence to support the following statement? More than 10% of U.S. adults have hyperthyroidism. Okay. Our confidence interval is 7.9 to 15.1. Agree? 10% is within that region. Agree? So this does not support it because 10% is within our confidence interval. Now, if we were to say, hey, I would like to say that 7% or more have this particular disease, that would be something you could say because it's outside of it and you're talking about a greater value. So number 5, no, we can't make the conclusion because 10% is within the confidence interval. The confidence interval being 7.9% to 15.1%. Make sense? And again, just realize that we are 95% certain that if we really did our stuff, we would get anywhere from 7.9% to 15.1% and anything in between. And it doesn't mean that what's more in between is the better answer. It just means, hey, it just means that what we got here. Oh, I have this dude. All right. Caden, says your ballerina outfit's ready to get picked up, okay?
So if you make it for me because you think ballet?
No. I think that's kind of cool. All right. And then, is the sample size large enough? Okay, so when it talks about the sample size being large enough, this is number 6, we have to do the n times p, is that greater than or equal to 10? And then the n 1 minus p, is that greater than or equal to 10? So our sample size was 400. So is 400 times 0.115 bigger value than 10? Yes, it is. And then is 400 and then 1 minus 0.115, is that bigger than 10? And if you did the arithmetic, you'd find it to be bigger than 10. And it doesn't matter how much bigger than 10 it is. So both of those satisfy it. So we could definitely say yes, we have a large enough sample that falls within that region. So the sample size is indeed large enough to meet the normality assumption. Okay. Now, a lot of people sometimes get stuck on this because you're still reverting back to, I have a sample size bigger than 30, therefore it should work. That is correct until you're dealing with percents, and then you have to make sure that those percents fall into this category. Okay, so you could say a third thing saying n is greater than 30, so yeah, that's great too, but that's not the whole reason. Okay, and then it says state the critical value. The number am I on? 7?
7.
I no longer show it on my board, so I have to move my screen. Hey, that's yours. Number 7, state the critical value for 95% confidence. What does this measure? Ooh. Anyone want to take a shot at that? I'll do it. So for problem number 7, my keyboard's just getting in my way. So for number 7, 95% confidence interval. So 1.96. Okay. So this 1.96 is basically the standard deviations. But remember, standard deviation when it's written as a decimal is actually a z-score. Okay. You need to be plus or minus 1.96 standard deviations or z-scores away to capture the 95% of the area. So if we made a normal distribution, we went right or left 1.96, that would you would find the area under the curve is rounded to 95%. And then state the margin of error. What does this mean in the context of the question? Okay. Where did we get that from? Oh, so the margin of error on this one would have been where we took the 1.96 times the 0.0182. Remember, we got this from our inverse CDF. Okay, if we multiply those together, that's going to come out to 0.036. Okay, so we are 95% confident we're 95% confident that our estimate of 0.115 is accurate to within 0.036. Okay. Was somebody just standing behind me? Like someone came in and, okay. Oh my gosh. Thank you. Like I thought I was totally losing. Well, I've already lost my marbles. So things you could change on this is you can change this to 3.6% if you wanted to. You could change this to 11.5% if you wanted to. So any of those iterations are fine. And then explain briefly what would happen if the margin of error of the confidence level is increased to 99%. So we go from 95 to 99%. So on number 9, our 95% has a certain width to it, like this, as far as if we had a normal curve. Okay. If we went to a 99%, this normal curve gets really wide. It makes it wider. Okay, so when you start getting to the higher percents, and again, that's one of the silly things I've tried to convey to you guys, is the general public will see the higher the percent of something, the more they're going to, you're like, oh, look at that. They haven't, they look and see a 99.9 that, if you stop drinking cow's milk, that your bones actually get stronger. People are like, oh, I'm giving up cow's milk. There goes the dairy farms. That's not actually true. 99.9% or 99% or 95%. It just becomes a much wider type of error that can take place.
So wait, the margin of error doesn't change?
Well, that 1.96, it becomes bigger. It might become like 2.15 plus or minus 2.15 or something like that. Okay. And then number 10 is from a random sample of 50 tax returns filed with the IRS, 17 of them contain errors. Construct and interpret a 90% confidence interval to estimate the percentage of tax returns with errors. Oh, these people, tax season's among us, right? Hope the IRS doesn't bust us. So the first thing I want to do for number 10 is figure out the percent. So they said 17 out of 50, which comes out to 0.34, which is 34%. So they're showing 34% tax returns have errors. Okay. So that 0.34 is going to be plus or minus our normal distribution, inverse CDF, halfway to 100, times the probability minus the probability over the sample size. Okay, I kind of abbreviated that because
What does that say though?
normal distribution and then the inverse CDF.
Oh.
Okay, so that's where we have to use Desmos to make sure we go right with that. All right, so
The normal distribution is 0, 1, right?
yeah. So you're gonna plug that into Desmos. So if I go 90%, what's halfway to 100? 95. Okay, which is 0.95. Agree? So this is we want to capture the middle 95% of the normal curve. NC we'll call normal curve. Okay, so Desmos time. I'm so excited. It's like stir up. I ain't that excited about it. I know you're not, but that's okay. All right. So jumping on here, I'm going to change halfway to 100 on that was 95, we said. Okay, so normal distribution, 0, 1, because we don't know the parameter, the mean of the population, and 1 because we don't have standard deviation given, inverse CDF. We were looking for 90%, so halfway to 100 from 90% is 95. So we're going to 1.64. Okay, so excuse me. What the hiccups? I said 1.64, right? Okay, it says 0.34 plus or minus that 1.64. And then I have our percent. So we have 0.34, 1 minus 0.34, divided by our sample size of 50. Is that what it was? So if you do this arithmetic, this will come out to basically 0.34 plus or minus 0.11. So we're going to go from 0.23 to 0.45, or we could make them as percents, 23% to 45%. Okay, so what does this mean in the context of our problem? We are 95%, or excuse me, we are 90% confident, okay, that if we redid this same random sampling techniques of 50 tax returns, that we would get anywhere from 23 to 45% of them would be incorrect. Okay, if we changed it to like a 99%, that 23 to 45 is much wider. It might go from, say, 11% to 65% or something like that. I'm just spitballing it. I'm not getting exact. And then last one, it says, according to a random sample of 600 households, 360 of them had a television tuned to the Super Bowl last year. Oh, this is exciting. Right time of year for the Super Bowl. I know you're all excited about the Super Bowl. Probably going to tune in just to watch one of the teams lose. Not sure which team you guys want to see lose, but I hope the Buccaneers lose. I'm kidding. So, trying to figure out if the Buccaneers are in the Super Bowl. They're not.
I'm actually boycotting this.
It's not the Bills.
They're
Chiefs, Eagles.
boycott the Super Bowl this year.
Huh?
Boycott it this year.
Boycott it?
Yeah, don't let Taylor Swift get all the attention. It's the only reason the Chiefs won, actually.
That's true. That's true. And I'm sure you can bet the over-under on the number of times Taylor Swift is shown on camera.
100%.
So
You always.
I hope they break up. That way Mr. Meow has a chance at dating her. All right.
Number one off.
All right. So we're going to say 360 out of 600 homes. If I do that math, it's going to come out to 0.60 or 60%, I believe. Someone double check my math. Is that right? 360 divided by 60 is 60%, I hope. Let's see, 36 over 60, 6 over 10. Yeah, it is 60%. Yay. All right. So we have our 0.60 is going to go out front. Plus or minus. This is our normal distribution dot inverse CDF. Okay. So, friends, we are doing a 92% confidence interval. What's halfway to 100? What's halfway to 100? Halfway from 92 to 100. What's halfway? 96. So this is going to become 0.96. And then times the square root of the 0.60, 1 minus 0.60, divided by our sample size. It was 600, I believe. All right. So back Desmos. So we're plugging in 0.96. So we can just kind of keep our Desmos alive, and we'll change this from 0.95 to 0.96. So now we're at 1.75. So 1.75. All right, so 0.60 plus or minus 1.75 times root 0.60 times 0.4 divided by 600. If you did, watch your order of operations, please. So that becomes 0.60 plus or minus 0.035. So that says that 0.565 to 0.635, or you could say 56.5% to 63.5%. So that is supposedly, if we were to do another random sample of another 600 random households, that we would find that between 56.5% and 63.5% would be the average of the new sample. Yay, we're all done with this. Hey, put your names on those. So we are on 5-8. So a 1 mean Z interval. is similar to the structure of a one proportion Z interval, which we just did. However, the mean sample have different standard error procedure as outlined by the formulas. So in this case, we're going to have standard error is equal to little weird Greek letter. It says, once again, the Greek letter symbol sigma, that's a lowercase sigma, stands for the population standard deviation. We must know the population standard deviation. Okay, so this is the population standard deviation, which makes this a little bit shorter when finding the standard error, which is great. Okay, so the point estimate is simply the sample mean, the margin of error becomes the critical value multiplied by the standard error. So the margin of error, MOE, or MO, we still have that Z star, which this is the Desmos. And then that's going to be times this, rather than the big square root of P times 1 minus P over the sample size and the square root of that. So it's a little bit shorter. So they give us this example. It says a company develops a test of leadership skills. Oh, we like leaders. All right, the test is given to 50 applicants for the job. The average for a test score is an 84. Assume that the test developers know that the standard deviation for all of these tests is 12. So in this case, they're telling us the population standard deviation is 12. Okay, they gave us that. I don't know how they know it. They're just saying they know it. So it's just creating 90% confidence that captures the average test score. Okay, so what we have to do on this is the same thing we've been doing. So in order to get our margin of error, we are going to find our Z star, and our Z star is going to be the normal distribution 0, 1, period inverse CDF, and then halfway to 100 from what was given. So they told us they want us to create, if we're creating a 90%, halfway to 100 means that this is going to become 0.95. Okay? And then if we do the math there, it will work out nicely. So we have to figure out that inverse CDF. And then once we're done with this, this gets multiplied by the 12, our standard deviation, over 50. So this is what's going to get multiplied by it. All right, so Desmos again, our favorite helper of the class. Weren't for Desmos, I don't know if I would like to teach this class. All right, so inverse CDF, I'm going to plug in 0.95. So it looks like 1.64. Okay, so our Z star value is 1.64. That means that 90% of our area under the normal curve with 0, 1 is going to work out very nicely. Okay, so if you do, go ahead and do this math. So if you plug in the 1.64 right here, that's times 12 times the square root of 50 comes out to 2.79. And then that basically says that we are 90% confident in our estimate of 84 is accurate within 2.79 test points. So that means 84 plus or minus 2.79, so from 81.21 to 86.79. That is, we are 90% confident that the true average leadership test score is between the scores of 81.21 and 86.79. Okay, does this make sense? And that was a quicker way to look at that. Okay, so I want to friends. Tomorrow we hit 5-9. Friends, I hate to do this because it's more work on my part. No, I think we can do it. I think we're good. Yeah, we're good. Yeah, because I crossed off a couple of the questions on this. Okay. No, it was gonna be a Thursday, but I won't be here, so you know, it was one on Thursday. I was just, because there's 2 sections left, but I realized when I looked at the last section. All right, that is all that is on for 5-8. So if you would like 5-8, we will go over tomorrow, and then we'll cover 5-9, but actually go over 5-9 tomorrow, and then Thursday we will do our test, in which I won't be here. There will be a sub. So that's all I have.